Hi there, my name is Raymond Doe, and welcome to my Physics 2211 Lab 4 video on oscillations. I hope you enjoy. The purpose of this lab is to observe, model, and analyze the change in energies of a spring mass while in oscillating motion in an arcing circle. To do this, we must first become familiar with the fundamental principles relevant to this lab, such as kinetic energy, gravitational potential energy, spring potential energy, net force, as well as the velocity and position update formulas. All of these equations and concepts will aid us in determining the verification of the energy principle from which derives the conservation of energy. By the end of this video, we'll be able to graphically visualize how, while the energies involved in the motion of the spring mass may fluctuate, the total change in energy equals zero, which of course, change in total energy being zero, satisfies the energy principle. Starting with my tracker data of my observed experiment, it is always important to note my systems and surroundings, those being the spring, earth, and mass, along with nothing else. To your right, you can see images of my tracking markers of my spring mass and circular motion, the graphical modeling of the x and y components of that motion, taking note of their oscillating nature, and lastly, the table of my numerical x and y values, which I then place into an Excel sheet and convert it to a CSV file. Here, we take a look at my GlowScript computational code in which I have labeled and implemented my initial conditions, those being a mass of 0.402 kilograms, gravity, of course, being 9.8 meters per second squared, my initial velocity being 0 in all directions, and my initial position being at the coordinates displayed. Along with those values, you can also see where I have employed the fundamental principles discussed earlier with the goal of calculating the total change in energy, which will require the summation of all forces involved. Taking a bit of time to explain my code further, to the top right, this portion of code establishes the forces, kinetic and potential, that we will need in order to compute the total energies acting on our spring mass. And on your left is a while loop that computes the net forces as well as the change in all energies incorporated in the above portion during the time interval recorded by tracker, which was 8.8 seconds. This slide simply exhibits my resulting graph for all forces and the motion of oscillations in the x and y directions of my spring mass. Potential errors in this lab approach may be found in external forces acting on the spring mass due to an open system, meaning that we are working with non-ideal conditions, or inconsistencies in the motion of my mass in my tracker observation. We're firstly asked if the results of our experiment satisfy the energy principle. Well, based on my graphical results, the energy principle is satisfied as the change in energy delta E represented by the horizontal orange line remains zero throughout the entire measured time interval. This means that all energies are conserved. Next, we are asked to discuss the differences in oscillation periods between the x and y components of our object. The average period of oscillation in the x and y directions I determined to be 1.78 seconds and 1.51 seconds respectively, resulting in a difference of 0.27 seconds. Considering the period of oscillation t is vital for the calculations of the spring constant k, it can be reasoned that inconsistencies in this data could lie in spring potential energy, as not only the k is affected by t, but also the relaxed length L naught. Thank you for watching and have a great day.